Okay, thank you very much. Very interesting workshop, very good timing in these scary times. So very good initiative by the organizers, and thanks for letting me participate. So this is new work by me and Frank Ball and Peter Trappman. The manuscript is available on Archive and medRxiv in case you want to have a look at it. And it involves herd immunity. So talking about immunity, I heard today that Spain had only 5% testing positive on antibody tests. Surprises me very much. In Sweden, there was a test reflecting the situation in late March. Sorry, not in Sweden, but in Stockholm. It was a random sample, and we had by then 10% testing positive. So I'm not a specialist at all in virology, but I'm surprised by the variation, and I'm even more surprised by the few random sample tests that are done for antibodies. So if someone has any comment on that at some discussion, I would be very interested to hear why are not countries testing more random samples to find out what fraction are carrying antibodies. But this talk does not, this is a model talk, there is no data involved. So I'm not claiming that the herd, what the current immunity level is in any country, but what we are investigating is at what level does herd immunity arise. So think of the following situation. Consider this COVID-19 outbreak taking place in a country, perhaps your favorite country, and suppose that you have some type of mitigation or lockdown going on. And by now, the plan is to gradually exit this, hopefully not having many more infections, but still probably there will be a few more infections. And the question is then, if this goes on, so suppose that there is no vaccine available, so more and more immunity is built up, then the question is, at what level is herd immunity reached? And suppose that we know what R0 is. I will take 2.5 as an example, but that it's not that I claim that R0 is 2.5, but you can ask exactly the same question for another R0. I also assume that immunity is induced by the disease. That is a different topic, which I'm not a specialist in at all. From what I understand, most people think that immunity comes after infection, at least to nearly everyone, and lasting for at least half a year or something. But in this talk, I'm just assuming this to be the case. So it's not that I claim this is for certain, but here we assume that you become immune after you have had the disease. So at what level, when will herd immunity come? How many will have been infected but before herd immunity has been achieved? And the classical answer is that herd immunity is obtained when a fraction 1 minus 1 upon R0 has been infected. And if R0 is 2.5, this is 60%. This is a classical result. I'm sure most of you know it. It comes from vaccination considerations. If you vaccinate 60%, then the whole community is protected from future outbreaks. However, this result relies on, it comes from vaccination consideration, and in that situation, the immunization is induced by vaccination, and most often it's considered to be uniformly distributed in the community. However, when disease spreads in a community, immunity is not distributed uniformly. So the answer to this question is not that herd immunity is obtained when 60% have been immunized by infected. Instead, the disease-induced immunity, which I denote by HD, as opposed to the classical herd immunity coming from vaccination considerations. And this disease-induced herd immunity will occur at a substantially lower level. exactly which level, we don't claim to know. We have a toy model, which I will explain, and in that situation, it occurred around 40 to 45% for this value of R0, but we are not claiming that this is the actually true value. So that's up to discussion and future research, I think. Our result is very new. Independently of us, and a few days before us, Gabriela Gomez and co-workers made the same type of observation, but for a somewhat different model. In their model, the heterogeneity that she considered was only in terms of susceptibility. So each individual had some type of random susceptibility, and depending on how much randomness there was in this susceptibility, she got even lower bounds, even lower values for this herd immunity level. In fact, for one scenario which they analyzed, the herd immunity level was as low as 10 to 20%. It's not that she claimed or they claimed that this is the true value either. So I think none of us claim that this is the true or that is the true, but I think both of these groups claim that the level is substantially lower than the classical herd immunity level. So what is the heuristic explanation to this? And I sort of alluded at it already. So when you vaccinate, vaccinees are selected randomly, so immunity is distributed uniformly in the community. However, when the disease spreads in a community, those individuals that are highly active or social are much more likely to get infected. So once they have been infected, the remaining individuals that are still susceptible are less socially and outgoing. So the remaining people after an outbreak during mitigation scenario, the remaining population is less socially active than the typical individual was before the outbreak. So in a sense, immunity is distributed more efficiently when it is distributed through an outbreak than when you vaccinate uniformly. It is not distributed optimally, if you want. There is quite a lot of literature about optimal vaccination policies, so it is possible to immunize even more efficiently than what is done during the spread of the disease, but that's a different topic. So is this a new result or not? Well, there is quite a lot of knowledge from dating long back that after an outbreak, immunity is distributed more efficiently than uniformly. That has been observed by many papers. Here are a few references. But at least as none of us, me, Frank, or Peter, but also the other group, have seen anyone sort of make use of this observation for the COVID-19 situation. And I think the reason is that COVID-19 is the first time, at least in modern times, where there is a pandemic going on, where all countries have reduced spreading, so that the outbreak after restrictions are on will be much lower than it would have been if we would have done nothing. So the only situation, I think, where fewer people have gotten infected than they would have if nothing was done is by means of vaccination. And then our comment is not relevant, because if you vaccinate, immunity is distributed uniformly. So here is the model that we use to sort of make some numerical computations. So we have divided the community into 6 age groups, and what fractions of the different age groups and how they mix. We have taken from the literature a paper by Jakob Alinga and co-authors. I think I know that Miriam Kretschmar is one of the co-authors as well. So at least she was here yesterday, so she might be able to say more about this. But this is based, this is based on studies. I don't social studies, I think, how people mix. So we have taken mixing from this literature, but on top of that, we have also divided each age group into 3 different activity levels. So we assume that within each age group, half of that age group is what we call normal active people, and then 25% are less active. And how much less? Well, we chose to say that they are half as active as the normal one, and the other 25% are more active than the normal activity group. And how much more? Well, we chose that they were had double activity. It's not that we claim that this is a fully realistic scenario of how reality works, but somehow it catches the effect that at least I think is present in disease spreading, that some individuals are much more outgoing and others are less outgoing. Also, in a sense, this type of heterogeneity within age group does capture features similar to those of network characteristics, where some individuals have high degrees, many have moderate degrees, and a few have low degrees. So it somehow is in the spirit of networks, I would say as well. So this is a simple model, 6 age groups, each age group divided into 3 classes, so in total 18 classes. And it's a multi-type epidemic. It's quite easy to determine the basic reproduction number. That's the dominant eigenvalue of the next generation matrix. It's also possible to derive equations for the final size. It's just, well, it's 18 equations, but the structure is not all that bad. And to solve these equations numerically is very quick if you have a good programmer, which we did in Frank. So that's quickly solved. So that was a model. And how do we model prevention? So what we did was that we assume that, and this can of course be criticized, that we're not claiming that this is the truth either. So we assume that the preventive measures were such that all mixing rates were reduced by the same factor. So the mixing rate between highly active elderly people was reduced to, let's say, teenagers was reduced by the same factor as the mixing rate between adults and adults. With this assumption, the new reproduction, the effective reproduction number, is alpha times the original reproduction number. And of course, if this alpha is smaller than 1 upon R0, the epidemic stops. But that's not the situation we are treating. We are treating a situation where there is still some spreading. So the simplest situation is that we considered was that we suppose that the restrictions start very early, approximately already from the start, and we assume that they go on until the end of the epidemic. Later on, we will make some more realistic scenarios. But anyway, if the restrictions are on from the start to the end, then you can think of, then it's really this epidemic with this reproduction number that is the outbreak. So we have the final size equation to solve this. And then we looked at the following question. What is the smallest value of alpha that gives herd immunity after the outbreak is over? So if alpha is equal to 1, then we are in the original basic reproduction number, which let's say is 2.5. So after an outbreak with alpha equal to 1, then of course we have herd immunity because the outbreak has taken place with R0 equal to 2.5. If alpha is, let's say, well, suppose if alpha is rather small, then there will be a small outbreak. And if we then relax restrictions, there is high risk for a second wave. So we're sort of finding what value of alpha that is exactly on the border of giving herd immunity for the original basic reproduction number. And that value we call alpha star. But we're even more interested, we're not all that interested in this numerical value. the most interesting thing is at this value, so suppose we have an outbreak with restrictions of this order, then the question that we have analyzed is how many will have been infected after this outbreak has taken place. The answer to that is what we call the disease-induced herd immunity level. So we find at what preventive measures you exactly obtain herd immunity, and then we ask how many people are infected in this situation. And here is a table describing this for 3 different values of R0, 2, 2.5, and 3. Maybe we should have taken 4 as well, but this is what we did. And under a few different population structure, under homogeneous mixing, there is no difference between the two, the classical herd immunity level and the disease-induced. Then we looked at the situation where there was only age structure, but no heterogeneity in terms of activity within each age group. We looked at the situation when there was no age structure, but only 3 different activity groups. And then we looked at what we think is the more realistic scenario when we have the age groups and the 3 different activity groups. And let's only study our main example, 2.5 in this situation. And then the classical herd immunity level says that 60% has to be infected before herd immunity is obtained. Whereas for this model, the result was that 43%, it was enough with 43% getting infected to obtain herd immunity. So this, what I said up until now, was assuming that the preventive measures were initiated very early on, already from the start, let's say, and they were kept until the end of the first outbreak. A more realistic scenario is, of course, that the restrictions are put on after a while, and then after a longer period of time, some type of exit strategy is done. So in the second situation, we looked at the time evolution, and then we used the deterministic SEIR. I'm not sure we used the best numerical values for the latent period. My impression is that the epidemic is slightly longer than seems to be the case. So maybe we took slightly too long values here, but it's more of an illustration. Anyway, the epidemic was started February 15. At March 15, restrictions were put on, and they were lifted only June 30. So with a quicker epidemic, this date would have been earlier. And first, we studied the situation when all restrictions were lifted at once. There will be one slide where we also look at gradual lifting of the restriction. And we did this for 4 different values of alpha. So the blue curve is when there was no restrictions at all. The red curve is when the restrictions were 20% reduced, reducing the reproduction number by 20%, reduced by 40%, and reduced by approximately 50%. So we see that there is here, this is where restrictions are put in place, and here is when they are ending. And we see that there is a second wave in this scenario, whereas in the yellow curve, which has 40%, there is no real second wave. So this is the incidence, or I think it's actually the fraction of people being infectious, which is close to the same as the incidence. If we instead look at the accumulative number of infected people, the curve looks as follows. So here is where the restrictions were put in place, and here is where they were lifted. And we see that, in fact, this strategy is better. So having slightly less reductions is better as compared to very strong restrictions and then suddenly lifting them. Of course, no country is doing this strategy. But anyway, we see that, well, they're not horizontal yet. This one seems to be close to horizontal. This is not quite horizontal, but I think it stays below 50%. And this is for the situation when R0 is 2.5. So the classical herd immunity level is up here. So we see that both of these end up with a lower fraction affected than the classical herd immunity level. Then a final slide, which I had in a, not in a EPS format, and I wasn't able to make it nice, look as nice, but here it is. So this is for a gradually exiting strategy during all of the summer. So I think we start lifting restrictions here, and I think we end lifting restrictions here or something like that. And then we see that at least this yellow line looks more or less horizontal. And now I can't see because there's some names here, but I think it ends up somewhere around 45%. So clearly below the classical herd immunity level of 60%. I think this is my last slide. Yes, so our main result is then that the disease-induced herd immunity level is substantially lower than the classical herd immunity level. How much lower, that we don't claim to know. So we encourage people to look at sort of more realistic models, perhaps doing bigger simulation studies to investigate this more. But I think including individual variation within age groups, I think that is crucial for realism, to admit that not all individuals, even within a certain age group, behave identically. In our model, we did not include several different types of heterogeneities. We did not have households, we did not have schools, we did not have workplaces, no spatial aspects. We have, where I have, but I think also Peter and Frank have thought a little bit about this. What would be the effect if also these things were included? And at least my impression is that that would make the difference bigger. So including households will make the difference between classical herd immunity and disease-induced herd immunity even bigger. But maybe there are other heterogeneities for which this is not the case, and we don't have a sort of formal proof saying that this is the case, but this is at least my impression, that including more of these heterogeneities will make the difference bigger. Of course, the assumption we had that 25% had half the activity and 25% had double the activity as compared to the normal ones, that is of course up to question. I don't know if that is exaggerating the social differences within age groups, or if in reality there are even more, that we don't know, or at least I don't know. So another assumption that we did was that the preventive measures acted in a proportional manner regarding all different types of contacts. In reality, that is not the case. For instance, I think most countries have a policy to isolate the elderly. So that means that this alpha for contacts with elderly will be much lower than contacts between others. Another type of preventive measure which does not act proportionally is closing of schools. Then it is mainly children that reduce their contacts. So the effect of this is a bit more complicated. I think isolation of elderly will make the difference even bigger, because typically elderly are not the most highly sociable. So if even fewer of them get infected, then they will make up a bigger chunk of the non-infected group. So I think that will make the difference bigger. School closing, I don't know. Working from home, I don't know either. And another thing which would go in the other direction, I think, is that suppose the situation is such that the highly sociable individuals, they reduce their activity, they reduce their contacts more than the not so social people. That will make the difference smaller between disease-induced herd immunity and classical herd immunity. So I think that ends my talk, and I'm happy to take any questions if there are any.
Um, Thank you very much, Tom. So I think in the interest of time, as we have one more presentation, we'll go straight to Rose. But what I suggest is that in the general discussion, or maybe as a breakout group, we can have more views on the role of immunity in exit strategies, which I think is, I mean, obviously is a very important topic.